We don't like electric spaghetti. Multiple antennas can work together to achieve some impressive results. The purpose of this video is to give you a qualitative understanding of how the array forms beams. We will use wires of an appropriate length plus another component to ensure that all the radar waves from a given beam arrive at an amplifier at the same time. Using wires and other components to manipulate the signals is called an analog beamforming method. There are 5 dipoles at the top of the diagram. In the dipole video, we saw that the dipole's radiation is strongest perpendicular to the dipole. Turning the dipole so it's horizontal results in this radiation pattern. That horizontal line just below the dipoles is a reflective metal backplane. You're seeing an edge-on view of this reflective metal backplane. The reflective metal backplane blocks the lower lobe of this pattern and protects the dipole against interference from below. So the dipole sees what's up in the sky and not what's on the ground. The dipoles have wires that pass through the reflective metal backplane and all the way down to those squiggly little things near the bottom. Those act to make sure the current flows properly down the wire. Those colored circles are directional couplers. They steer the signals coming down the wires to an amplifier so that the signals can be detected. Here come some electromagnetic waves from the top of the frame. They're just what we're looking for. Note that all the peaks and troughs in the waves align with each other. This means they are all in phase. The horizontal line at the bottom of the wave train is the wavefront. In the diagrams that follow, we'll just show the wavefront and not the squiggles or the arrow. The wavefront has encountered the dipoles. The wavefront induces very tiny feeble currents in the dipoles, shown as those white arrows flowing away from the dipoles. They'll be amplified later on. The currents are encountering the pink directional couplers, but it's intended that they go to the blue directional couplers, so the pink ones have been turned off so the currents can safely flow by. The currents turn the corner at the couplers and head for an amplifier, represented by that small green triangle. And look, we have a little blue blip. We've detected something. Hooray! Now we have some pink waves coming from the upper left. Let's see what the wavefront does when it encounters the dipoles. The tilted pink wavefront encounters the dipoles individually. It's causing a current to flow from the leftmost dipole. The wavefront causes currents in the individual dipoles as it passes over each dipole in turn. The leftmost dipole was encountered first, and so its current is farthest ahead. The pink couplers have been turned on, the currents turn the corner, and head for an amplifier that will appear in just the nick of time. And there's a pink blip. We have made another detection. Here come some red waves from another direction. You know everything that's going to happen, so we'll have an abbreviated look. The wavefront encounters the dipoles, induces currents that turn the corner at the red couplers, that then result in a detection when they reach the amplifier. So we're 3 for 3. The thing to notice about this is that the couplers are placed on the wires to match the tilt of the respective incoming wave trains. Thus, all the waves of a given wave train arrive in phase at the amplifier so they can add together. I'm going to pretend that this is a radar receiver array. This, of course, implies there is a separate radar transmitter array that I will not illustrate. I'll assume the radar transmitter and receiver arrays have a range of about 100 kilometers, or 62 miles. The round-trip travel time for this range is less than 1/1000th of a second. This means that in 2/10ths of a second, the transmitter can transmit 100 pulses like the wave trains we saw in a given beam. The receiver beams will also point for 2/10ths of a second in the direction of the given transmitter beam. The beam lobes have been placed above the array to help you visualize the situation. The receiver beam switching times will be synchronized with the transmitter beams. The array is doing the work of 3 different dishes. Let's start scanning. This isn't the only way to scan a beam across the sky. There are schemes that can sweep a beam across the sky by slightly changing the transmit or receive frequency. Another method uses devices called ferrite rings. The current passes through and around the rings, and this slightly changes the current's phase. Adding currents together with slightly changed phases for each has the effect of steering the beam. Let's add 4 more layers to our array. Now we have a 5 by 5 array for a total of 25 dipoles. From this angle, we're viewing the plane of the red couplers nearly edge-on, so it looks like a line. The problem with this is that there must be a wire between each individual dipole and every other dipole in the array. This would be accomplished by wiring together all of the output lines from the directional couplers for a given color. I've used only 3 beams for this example, but the rule of thumb is that it's possible to have as many beams as you have dipoles. So this array has 25 dipoles, so it would have perhaps a maximum of 25 beams. This quickly causes a big increase in the wire count. Each beam requires 25 directional couplers and their associated wires. 25 beams times 25 couplers per beam equals 625 couplers and a lot of wires. It's not a very flexible scheme because everything is hardwired. The radar and SETI arrays will each have many antenna elements. That would mean they would need many wires squared. Electric spaghetti. The solution to the problem of too many wires and the inflexibility of configuration of the array is digital beamforming. I'll produce another video for that sometime in the future.